Welcome to the NFS P&D podcast series. Today's session will be presented using Teams live event. It will be recorded and uploaded to InfoZone. Please join using a USB headset or computer speakers or KP issued smartphone. As a reminder, there's no dial-in telephone option. If you have any questions or comments, please submit them through the chat panel and they'll be addressed at the end of the presentation. If you want to receive AIA credits for today, wow, that went fast. I've got to take the auto timer off of that. But anyway, I have to read that announcement, whatever. Okay, so today is going to be pretty jam-packed. We have a lot of topics to cover. I'm going to rattle straight through the content portion of this and we'll do questions at the end. So please do type in your thoughts as we go. And then when we publish this, my intent is to publish 6 separate videos so that you can reference each one of them individually. And so each one of those videos, there'll be an average of about 10 minutes. So that's really the goal, is to have these 6 chapters of content. Okay, so chapter 1. In 2022, you're going to see new language in the Kaiser OPRs. And the A&E RFP requirements for plant maintenance work. And so in this section, I'm going to review that new language, what it means. The main bullet points are assessments, data gathering and analytics, contemporary calculations, and then sizing, and then options development. So this is what a Kaiser OPR looks like. If you haven't seen one, on page 1, there's 4 sections. The scope section, the design and performance outcomes, the key milestones, constraints, and then project goals. And the language that we're reviewing today is in the design and performance outcomes section. We've also updated or created, I should say, for 2022, some numeric energy goals for plant maintenance work. I'm going to show those throughout the course of this hour. This is the same language from that scope section. It's just blown up so that you can read it, and we'll start walking through it in the next couple of slides. So task A is assessments. This is a pretty traditional piece of scope. So you review the equipment data, do a field walk, and then write up assessments of it. All those items that are listed here in this bullet point list should be included in that write-up. So you've got your age of equipment, the overall infrastructure, physical condition of that equipment, and the infrastructure around it. And then reliability, age, condition, and if you have some reliability data, mean time between failure type of metrics, we can do those. We should also talk about repair costs and what the replacement marketplace is like, and the viability of ongoing service to a piece of equipment or a system. So I think we've all seen narratives like this. This is a pretty common piece of scope. Task B is to gather available data and use it. We're going to spend a lot of this hour talking about this. We always have utility data available, so monthly electrical, monthly natural gas, monthly water use, cost, weather metrics. So at a very minimum, we can calibrate our design ideas to that historical data to make sure we're in the right ballpark. We also have 15-minute interval data available from the utilities. We have to request that, but we should always request it. By the way, in some cases, we can get 15-minute or interval natural gas data, which is pretty cool. We always have weather data, historical weather data available to us. If the building has a BAS system, then we can pull it from that. But even if the building doesn't have a BAS system, there are a couple of websites that are readily available. You can pull down historical weather data from anywhere in the world. And then for electrical projects, we require load readings as part of the projects. And then, of course, finally, if your building has a building automation system, then there's this whole trove of data that we can be collecting and that we really should be looking at. We're going to talk a lot more about that. The bottom line here is that we really expect our designs to be driven by data. If there's data there, we need to use it. If that data isn't readily apparent when you start the project, then we need to go through the effort to collect it and then use it. So then task C, this is going to be new for a lot of design consultants. Most of our design consultants don't include contemporary calculations for their scope. In fact, I'll go ahead and say it. Design consultants never include this in their scope until we ask for it. But the way to think about this is that we should not assume that the previous design engineer's work was correct. If someone drew a set of plans 10 or 15 years ago, we're not going to assume that all of their numbers for all the zones were correct and still valid today. It may be that 75% or 80% of those are correct, but we're not going to assume that. We're going to validate that. So in this task, we look at the architectural floor plan as if it was a new building and do a set of cooling load calculations, heating load calculations, electrical load calculations, ventilation calculations, as if it were a new building. That's what we mean by a contemporary design calculation. If this building did not have a mechanical system, what are your calculations, or what would your calculations be today? Now, that does not mean that we're going to change the airflows in every room, but it does mean that we can compare the contemporary design calculations to the current state in the building. And there's going to be zones where we need more cooling or more heating or less cooling or less ventilation. And we want to know that, and we want to be able to walk through that to see where we can make changes and will make changes. Task D is to determine the equipment size, and I need to point out right away that determining the equipment size is pretty far down the list. Equipment sizing is not task A. It's not the first thing that we do. It's soundly down the list. And so saying that the equipment is replaced in kind is never an acceptable option. We want to size equipment based on the assessments, based on the existing information, based on those contemporary design calculations. This is something that comes up time and time again in our scope. Project managers will say, hey, just replace the boiler with the same size boiler, right in the top of the scope or right in the RFP. So on the Kaiser side, we're working pretty hard to correct that. So the scope that you get should not tell you that we're going to replace in kind. And then the final task of scoping is options development. We like to talk about the 3 R's, repair, refurbish, or replace. So for any system or component, those are the 3 things we want to look at. Can it be repaired? How long would a repair extend the life? Is there a major refurbishment or retro commissioning that can happen, or does this need to be replaced? And so this is where we would come up with a list of those options, do life cycle cost analysis if there's significant difference between the options that are on the table. And this last slide is just to show you the text about energy design targets for plant maintenance. We now have energy design targets for the plant maintenance projects, and we're going to talk quite a bit more about these in the coming sections. So to sum up, the scoping phase, our design requirement includes assessment of existing systems, pretty traditional assessment of existing systems, and then gathering data about the system, analyzing data about the system, performing a set of contemporary design calculations, and then and only then determining the sizing of equipment and developing options for the project. Okay, so that takes us to chapter 2, where we're going to talk about design validation and acceptance criteria. So for plant maintenance work, our requirement is that the engineer of record documents the expected range of operations for the system in a set of acceptance criteria. Those acceptance criteria need to be in the contract documents, and we are going to directly measure them during commissioning. So the design engineer says, at noon on Tuesdays, the fan power is going to be 8 horsepower, plus or minus a half. Then during commissioning, we're going to measure it, and we expect it to be 8 horsepower plus or minus a half at noon on Tuesdays. It's a really simple concept, falls into that category of simple but not easy. I'll tell this story. I always remember this story. Several years ago, I was having dinner with a couple of design engineers in San Francisco, and one of them was a mechanical engineer, another one was an electrical engineer. We had a nice dinner. There was wine, and at one point in the conversation, the electrical guy asked the mechanical dudes a question. He said, well, you guys know, right? If it's 10 o'clock in the morning and if it's 77 degrees outside, like, you know how much fan power should be in the building, or you know how much cooling power should be in the building, right? And I remember me and the other mechanical guy kind of looked at each other, and we were quiet for a second, and then we both started laughing and said, well, no, we don't know that, man. We don't do that calculation. We would really have to go in and look at the math and look pretty hard at that in order to figure it out. And I always remember that story because it dawned on me immediately that we need to, in order to validate that we have a design that works, we absolutely need to know what those values are, or what those ranges are, or when we fail. If it's 10 o'clock in the morning and 77 degrees outside, I need to know how much fan power should be used. I at least need to know the upper limit of that so that I can tell if I'm way over. We need to know how much cooling energy should be used. So it strikes me now that we tend to do energy calculations in annual units, kilowatt hours per year, or therms per year, or kBTU per year, or dollars per year. That's very much our industry standard. But on the ground, we need to check those in units of hourly. If we get off track in the first hour, then we're going to be off track for the first week, and off track for the first month, and off track for the first quarter, and we won't hit the annual target. We don't have a chance of hitting the annual target. So while our industry standard is to express our energy calculations in annual units, we have to be able to express them in hourly units and then check them in hourly units. So the good news about this is the same as the bad news about this, right? It's one of those dichotomies, right? The good news about hourly energy targets is that we will know in hour one of day one whether the design assumptions were correct. And then the bad news about hourly energy targets is that we will know in hour one of day one whether the design assumptions were correct. So to talk about the role of the designer, we've been doing these acceptance criteria for a couple of years, and we actually have a template that many of you have seen. We've used our commissioning agent for acceptance criteria, but we've come to realize, particularly in the last year, that the acceptance criteria have to be done by the design engineer. Nobody but the engineer of record can own these. What happened in 2021 was that we had acceptance criteria being changed during commissioning. So we had a criteria out there. Sometimes they were issued by the engineer, sometimes not. And then we got into commissioning and the numbers started coming in and they would be different than acceptance criteria. And so the commissioning team, just trying to move things forward, would move the number to some other marker and then pass that. So in 2022, we're implementing an acceptance criteria change process. Once the acceptance criteria are in the contract document, then if we need to make a change, we would do that the same way we would make any other change to a contract document. Engineer of record would issue a change with a reason, and then that goes out to the contracting team and the commissioning team. So here's a nice example of acceptance criteria in the contract documents. In this case, acceptance criteria right on the plans. I kind of prefer this. We've said that they can be on the plans or they can be in the specifications. I think it looks nice when they're on the plans myself. Another thing we've come to realize is that acceptance criteria and controls design is very much a team effort. In my day as a design engineer, when I had to write a sequence, the way that it generally worked is that I would drink 3 cups of coffee on like a Thursday afternoon at 4 o'clock, and then I would dive in and plow through it until 9 p.m. I try to imagine every possible scenario I could conceive and write it in, just caffeine sweating out of every pore. But ultimately, to be totally honest, that sequence was never going to work because it has to be a team effort. The controls vendor, the commissioning agent, the operations folks, the Kaiser engineering team, the equipment vendors, they're all stakeholders in those sequences. Those sequences need to work for everyone and they need to be understood by everyone. A big example of where we've seen this is rooftop package units. The sequence that I would write for a rooftop package unit, you know, on 4 cups of coffee, and then the sequence that actually arrives on a job site at the train unit, or for the train unit or the carrier unit coming out of the factory. Those can be 2 totally different things. And so that all needs to be hammered out and vetted out during the design phase. So it truly does take a village to build these. We've also established minimum acceptance criteria to demonstrate the design intent. And I don't mean minimum like minimum numbers here. I mean like a minimum quantity of acceptance criteria that's needed to prove out our design intents. We've come to realize or say that there are about 4 categories of acceptance criteria. You have your systems in control acceptance criteria, your turn down, turn up, turn down acceptance criteria, efficiency acceptance criteria, and then what we call the non-trended points or the more binary acceptance criteria. So for example, if we have a boiler, first you would want to see that the temperatures are in control. You'd want to see that the pressures are in control, the flows are in control. Those are the system in control acceptance criteria, which are really prerequisites to anything else. Next, we should see turn up and turn down. We should see turn down at night, turn up during the day. We should see turn down when it's warm outside and turn up when it's cold outside. And then we want to see efficiency. We should look at the BTUs in the heating loop, divide that by the BTUs in the gas line upstream, and we all want to see that number over 80% for a heating system. And then, of course, there are just some binary yes or no, check the box type of criteria. For a boiler, these would be things like failure modes. For an electrical system, there's a whole lot more of those non-trended acceptance criteria. So my group maintains a template acceptance criteria, and I'm emphasizing the word template. This is a template and not a standard. I'm of mixed minds about this. First off, I'm very glad we have it so our designers can lean on it. It definitely shows what acceptance criteria should look like. But on the other hand, we absolutely need design engineers to own their own acceptance criteria for their own designs. So if the template says that, you know, fan power is going to be a ½ watt a square foot, and the engineer of record puts that on their plans, then they really do need to check that and make sure that it's valid before they put that on the plans. If we get to commissioning and the system is using 6 times that, then we don't really want to hear, well, we got that number from the Kaiser template. We want to make sure that our engineer of record is putting that on the plans appropriately. And I think that's the end of this section. I have a junk slide here that doesn't belong here, and then we'll move to the next section. So that takes us to this section on assessments of HVAC systems. The design program requirement that we have is that we want our engineer of record to gather and assess data to determine the current system operations and the system deficiencies. We already talked about a list of data that's available for assessments, but in this section, we're just going to talk a little bit more kind of about the theory behind these assessments. And the main principle that I want you to walk away from and understand is this hierarchy and to work from the bottom up. So if you're doing an air handling system or a chiller or a boiler, the responsibility is to assess the existing systems from the bottom up. And so if we have a building where there's 5 zones that have cold calls and those 5 zones can never get warm, the last thing in the world we want to do is to install new boilers and new air handlers and new pumps and then still have those 5 zones with cold calls that can never get warm. That would be terrible. And we know it would be terrible because we've done that. We've done that more than once. So when we're designing a boiler or a chiller or an air handler, it is our responsibility to start at the bottom and start in the zones. Where are the hot calls? Where are the cold calls? What's causing them? Are there valve problems? Are there sensor problems, airflow problems, coil problems, control problems? Is it truly a capacity issue or is it something else? That's also true for energy. Where is the energy going? Are the zones turning off at night? Are we overcooling? Are we reheating? Are the control valves hunting? So start at the bottom, check the zones, find the deficiencies in those zones, and make the correction of those deficiencies part of the work of the project. Otherwise, we wind up in that scenario where those 5 zones that were problematic in the beginning are still problematic because nobody came along and fixed them. So this hierarchy is good for those comfort measures. It's also good for the energy measures. If we have a chiller, for example, that's running 24/7, it's probably running 24/7 because the air handlers are calling for cooling 24/7, which is probably calling for cooling 24/7 because the zones are calling for cooling 24/7. So again, start at the bottom and work up. The flip side to this, to take this concept and look at it the other way, if we don't assess the building from the bottom up, then what we're really doing is taking on assumptions for the levels that are sort of below us within the project. We would be assuming that all the zone calculations are correct. Whoever drew those plans 15 years ago or 20 years ago, we would be assuming that all their work was right, all the zones have the right amount of heating and cooling, all the turn down settings are correct, all the sizing, the air handlers are sized correctly, the heating and cooling coils and the air handlers are functioning well, et cetera, et cetera. So when you look at it that way, It's a tremendous lot of assumptions, and in 9 out of 10 cases, at least some of those assumptions are false. In fact, often many of those assumptions are false. So in the grand scheme of things, there's more risk in not doing these assessments because of just the sheer list of assumptions that we take on when we don't do them. So that's my cute summary slide here. We're either going to assume that everything in the building works below the scope of our project, or we're going to assess and find out what's working and what's not working. So our design program requires our engineer of record to gather and analyze data to determine the current state of operations and deficiencies. In this section, we talked about that hierarchy of assessments to make sure that we're always assessing what's necessary. So that'll take us to our next section, chapter 4 here. And in this section, we're going to look at data. We're going to do some examples and try to get into this data-driven style of thinking here. And so to start off, this picture is from, this is my favorite scene from the Ron Howard film Apollo 13. NASA engineer walks into the room with a load full of stuff. And he goes, listen, we got to make this fit into the hole for this using nothing but all that. And then my favorite line in the film is voice number 3 down at the bottom there that says, all right, we better get some coffee going too, somebody. And I love this because I want to emphasize that data analytics is a creative process. As engineers, we all love linear thinking, but when we get a pile of data and we need to make sense out of that, nothing but creativity comes to that job. So rule number 1 in existing buildings is that you are never going to have perfect data. You're never going to have the data that you want. The data will always be flawed. You're always going to wish that you had a sensor or a meter 5 feet away from where you actually have a sensor or a meter. So there's always going to be problems with the data. We can't let that stop us from being creative and getting to answers. We have to use the data that we get and make good with it, right? So the first data set we will always have is a monthly utility bill. And there's a couple big things you can do with the monthly utility bill. The first one is you can check for a relationship. When we download our monthly utility data, we also get cooling degree days and heating degree days for those months. Now, it's very common, I'll tell you straight up, to find no relationship. In other words, the conclusion at the bottom of this slide would say the monthly electrical use has no relationship to the monthly cooling degree days, or the monthly natural gas use has no relationship to the monthly heating degree days. That happens. The first time I saw that, my head exploded because it stands against everything I've ever learned as a mechanical engineer, but it's actually quite common. In this example, there is a relationship. We're looking at a linear regression of the relationship between heating degree days and natural gas use. This relationship is reasonably strong. R squared is better than 80%, and the line has a slope. And it tells us a couple things. The y-intercept of this relationship gives us an idea of how much reheat is being used in the months where there's no heating demand. So in the summertime, you can take that y-intercept number and divide by 730 hours a month in the building size. And in this case, you'll see that that's an average of 24 BTU per hour per square foot for every hour. That's just happening in the building, probably in the form of reheat. And then the slope of the line, the actual slope of it, how high it goes, tells us how strongly this building responds to cold weather. In this case, every heating degree day in the month adds about 0.02 BTU per square foot. Now we can take this kind of thinking further. When we do a heating load calculation, traditionally, there's 2 components. There's an envelope component that you call UA delta T, and then there's a ventilation component that's 1.08 CFM delta T. If we combine those to a single scalar factor, it would be kind of a UA plus 1.08 CFM all multiplied by the delta T. So what we can do is we can look at the weather data for a few months, get the hourly weather data for a few months, and then merge that against the natural gas bill data for those months. So you use a heating temperature of 70 or 68, in this case I'm using 70, and solve for K. And that is actually in units of BTU per hour per degree less than 70. In this case, K is about 20 BTU per hour per degree less than 70 in natural gas. It's the same formula that we use for a heating load calculation, a theoretical heating load calculation. But in this case, rather than using the building architecture to come up with U and A and CFM and 1.08, we're using the real data from the weather to derive that historical relationship. And I've showed this example for heating. You can do this for cooling. It's slightly more complicated. It's a bit of a more mathematical gyration before you get to the regression, but it's the same process. Another piece of data that we can pretty much always get is 15-minute interval data from the utility. We can request that for any building, and I'm going to say 9 cases out of 10 or 95 cases out of 100, we can get 15-minute utility data. And that gives us a bunch of opportunities. The easiest way to get into data analytics on utility data is to use this free tool. It's called ECAM. It's by PNNL. ECAM stands for Energy Charting and Metrics. If you've never seen the tool, check it out. It's an Excel spreadsheet. It's 100% free. And on their website, they have about an hour and a half worth of training videos. Those are pretty good. And you can get some charts like this, you know, weekdays, Saturday, Sunday, holidays, plotted against hours per day. So we can immediately start to connect those values to our design. In my mind, I always take those numbers and divide by square footage because our load calculation assumptions are usually in watts per square foot when it comes to things like plug loads and lighting loads, etc. Another source of data that we have are the diagnostics. Hopefully many of you know that we have an enterprise fault detection and diagnostic system called Clockworks. So for buildings that are connected to Clockworks, start with the diagnostics. Clockworks runs diagnostic tests every day, every week, every month, and it produces faults. There are comfort faults, there are energy faults, and then there are maintenance faults. So if you simply pull down 1 or 2 months worth of fault data from the building, that'll point you to all the areas in the building that have problems. It'll show you which zones and valves and coils and pieces of equipment are having problems. And it gives you a pretty good list, and it tells you the frequency of those problems. Now, if you're not connected to Clockworks, you can get a similar list from the BAS system itself. Every building automation system has a list of alarms in it. That's one of the main features of building automation systems. So there's lists of alarms that our building engineers get every day. So by simply gathering a couple of weeks, or better yet, a couple of months worth of those alarm lists, that will give you an inventory of where the problems are happening in the building, which zones are having problems. So then we get into actually looking at diagnostics based on trending data. And once you get into this level of diagnostics, histograms are probably your first and best friend. So there's a list of diagnostics that we can do there: unoccupied hours, undercooling, underheating, overcooling, and reheating. And in most of those cases, you can look at the data with histograms. So we always want to do the unoccupied condition. I call that the 4 a.m. versus the 4 p.m. test. What are the zones doing at 4 a.m. versus what are they doing at 4 p.m.? Most of our zones don't need cooling or heating at 4 a.m. and so you should see a significant difference between what's happening there. Then we have undercooling and overcooling tests. These again can be simple histograms of damper position or CFM and valve position. The orange and red histogram down at the bottom there is an overcooling test. You can see that this zone spends a significant amount of time at 75 to 90 CFM and then another significant amount of time up at about 130 CFM. And in both cases, the valve position, the average valve position at those CFM ranges is quite high, right? It's at 80%, which is to say that this zone is pretty much perpetually reheating or very frequently reheating. That's something we should look at during design. Then we get into fan systems. If we have trend data on fan systems, we can do a similar set of diagnostics. In fact, the same list. We want to do the 4 a.m. and the 4 p.m. test. Every air handler should be at some kind of reduced state at 4 o'clock in the morning. It may not be off, but it should be at some sort of reduced state. However, as you go through our building portfolio, that will frequently not be the case. And then the undersizing and oversizing tests are similar. If you have a fan that's sitting at 100% speed and not making pressure set point, that would indicate undersizing. Oversizing can look very much like what you're seeing on a screen. If you have This fan never gets above 75%, and it spends a huge block of time down at 25% fan speed. So as designers, we really want to pay attention to the sizing of this. The other thing you can do with a fan system that I like to do is to plot it against outside air temperature. The smaller picture on this slide here shows the fan speed on the y-axis plotted against outside air temperature on the x-axis. And I'm going to use that example to point a couple things out. First off, just to look at that cluster of data, I want you to notice that it's not normally distributed. That data is not a bell curve. It's more of a multi-nodal distribution. So we clearly have this big node at 25%. So regardless of the temperature, whether it's 50 degrees outside or 90 degrees, we're spending hours at that 25% level. Then we kind of have this second node that's weaker that happens at around 40%. So when the fan speed does bump up, it bumps up to around 40%. And then we have these even weaker nodes that are kind of above that, 50%, 60%, and this other very weak node up at 75%. The other thing that I'll point out here that was surprising to me and maybe surprising to you the first time you see it is that the highest capacity number does not occur at the hottest temperature. As a design guy, this surprised me, right? I would have expected to see the biggest number on this chart line up over that 90-degree temperature range, but that's usually not the case. It's also common with heating systems. The peak capacity rarely, if ever, occurs in the actual coldest hour that occurs. So this is kind of a funky infographic, again, looking at a fan system. Another thing that's good to do sometimes to look at data is to sort the outside air temperature into 5-degree bins. So each one of these rainbows shows the distribution for a 5-degree band of outside air temperature. The black color represents the top 1% of points within that data bin, and the purple bar represents the top 10% of points within that 5-degree temperature range. And then the green bands right in the middle are the 40% to 60% data within each temperature range. And again, you can see the peak, which is about 11,500 CFM, occurs in the 85-degree band. It doesn't occur in the 100-degree band. And I would, of course, be remiss if I didn't tell you that the design airflow of this air handler, the scheduled airflow of this air handler is 23,000 CFM. So in a year's worth of data, it never even got to halfway, right? Another diagnostic that designers should be interested in is the variance around any controlled temperature or any controlled pressure. This type of analysis would apply to any controlled point, supplier temperature, pressure, water temperatures, etc. On this slide, we are looking at supplier temperature control. So I like to talk about this in terms of the quality of control. Again, I'll point out these are very often not bell curves. They don't spread out equally to both sides. And then often the numbers that you find in there can be difficult to wrap your mind around. In this case, we're seeing data spreading out to minus 12 degrees and plus 8 degrees on a supplier temperature control. It's important to look at these things for the reason that as you're progressing with design, you need to do one or two things. You're either going to accept that the supplier temperature control is this, and this is what it is, and that's okay, and we're going to proceed forward with design, or we're going to make a deliberate effort to do something to change this level of supplier temperature control. This is actually a similar example, but this is for a heating system. Some of the checks that we would do on a heating system are the checks that we would do on air handling systems. This one in particular is the supply water temperature control. And once again, that range is probably, it's not normally distributed. You can kind of see that there's 3 nodes within the curve. There is a node at right around 1.5 to 0 degrees. That's good. But then there's these 2 other minor nodes at -9 and +7. Which, again, we're either going to accept that or we're going to change that. Also on a heating system, this is a capacity check that we could look at. This is historical load in a heating system loop. And in this case, Since the data is not normally distributed, we like to use percentiles rather than averages and standard deviations. And so this chart plots the 10th percentile, the 50th percentile, and the 95th percentile for a heating system. Again, I would be remiss if I didn't point out that the peak load that we see is at 25 degrees rather than 20 degrees, and it's about 500,000 BTU, and our design was for I think a 3 million BTU boiler system. Right? Finally, this is a bit of a teaser here, but we can do things with existing zone data, like tabulate the room historical loads. We're going to talk about this in about 10 minutes, so I'll just tease it right now. What you're looking at here is a set of historical loads in about 17 operating rooms. But I really want everyone to learn that word, historical loads. So to recap this section, to go back to the example, I think that data analytics and data-driven design requires creativity. You're not going to have perfect data. You're not going to have the data that you want. You're not going to have a meter in the right location, but you will have data. You'll have data coming at you. And with that data, you can think creatively and learn a lot about the systems that move you into some sound foundations for design. Okay, so chapter 5. We're going to talk about design energy targets for the plant maintenance buildings. So first off, Kaiser now has design energy targets for work in existing buildings. The design requirement is for the engineer of record to evaluate against these targets and develop plans to get us to the targets. The way this is stated is it does not say that we need to meet these energy targets with every design. It's stated that we need to always assess our design relative to these energy targets and then plot out a path of what it would take kind of to get to these targets in the future. Now, the good news about these actual energy targets that you see in the table there is that we know that they're feasible because they come from our existing building portfolio. Each of these targets comes from very real examples. They are in our higher performing buildings, but they are absolutely feasible examples. So we know that they're possible. It's just a question of designing to them. That's where the challenge comes in. So the easiest way to look at energy targets, if you're a design engineer, would be to do it with an energy model. I'll stop right there and say that most of our plant maintenance projects, traditionally, our design engineers don't do an energy model or a load calculation at all. But if you do, then the process is simple. Every load or energy modeling software, including Trace, can output an 8,760 line report. So you take those results and sort them into fan power and cooling power and heating power and sort them by outside air temperature and then simply report them in the basis of design. What's the fan power at 55 degrees? What's the cooling power at 75 degrees? What's the heating power at 65 degrees, et cetera, et cetera. Just list them. It's that simple but not easy, right? But even if you do an energy model, you still have to look at your equipment schedules and make sure that the equipment that we're scheduling can meet those energy targets. And we'll talk through some examples here. This example is a 17,000 square foot project. The cooling coil has 70,000 BTU as sensible, 1 million BTU a total. That's 12.7 to 18.1 watts per square foot. So our target cooling energy use at 85 degrees is 2.2 watts per square foot, which is less than 20% of this coil capacity. Target cooling range at 75 degrees is 1.6, which is very low for this coil. So that right away tells us something. It tells us either this coil that we've selected doesn't meet the target. We're going to have vastly greater energy use at the 85 degree target, or we're looking at a coil that's going to potentially become unstable as we move down towards 75 degrees and towards the neutral condition. So in this case, even if we had an energy model that said we were going to meet the target, we would need to check this schedule and make sure that the equipment that we're scheduling has a viable selection at that target. Is this coil going to be fluttering, or is it going to be producing a 4 degree delta T down at the 80% condition? That's the kind of thing we need to always look at. Same example, let's look at heating. Again, 17,000 square foot project. And for heating, what we would do is we actually look at the air in the schedule We call that the sum of the zone minimum CFM, sum of the zone minimums. If it's a constant volume system, then like this one, the sum of the zone minimums is just the sum of the zones. In a variable volume system, though, the sum of the zone minimums is the sum of the minimum CFM in each zone. And then a way to calculate reheat is to assume neutralization of all that air at the sum of the zone minimums. So if it's 75 degrees outside and we have no setbacks, then we would be cooling all of our supply air down to 50 degrees. And in the worst case scenario, we would be heating it back up to 75 degrees to neutralize it. Well, that's 8.5 BTU per square foot. If we are using supply air setbacks, then we would be taking our outside air cooling to 60 degrees. And in the worst case, we're reheating back up to 75 degrees to neutralize it. Well, that's 4 BTU per square foot. Our heating target is 1 BTU per square foot. So in either case here, we're falling short of the heating budget, or we're not making the heating budget. But what if this was a VAV system? If the sum of the zone minimums could be quite a bit less, if they could be as low as 0.45 CFM per square foot, which is very reasonable in a hospital, in that condition, without the setback, we'd be at 2.5 BTU a square foot, and with the setback, we'd be down at 0.7 BTU a square foot, which soundly meets our energy target. So we'll look at fan power. Same example. Our fan power target at 75 degrees is 0.3 watts per square foot. At 85 degrees, it's 0.4 watts per square foot. This air handler is 25,000 CFM. There are 6 supply motors, 3 return motors. So the grand total of the brake horsepower is 1.9 watts per square foot. So this is way over our energy target by a factor of 5 or 6, right? In a constant volume scenario, what if this was a VAV system? If this was a VAV system, then we would again want to look at the sum of the zone minimums. In this case, that's 6,800 CFM. And so we would calculate the fan power that we would expect to see at 6,800 CFM. Couple ways to calculate that. You can use the fan laws. That shows you 0.04 watts per square foot. I've been told that the fan laws are less than perfect because they don't assume a pressure set point. So you could do the math and just run the pressure equation at 2 inches of pressure. And even in that case, you get 0.1 watt per square foot. So you'd meet the target with that. That, though, brings us to the idea of a viability check again. If the sum of the minimums on this air handlers is 6,800 CFM, we need to ask ourselves the question, is this 25,000 CFM air handler viable at 6,800 CFM? So there should be, in this case, it's a fan wall, so the answer is probably yes, but we do need to make sure that there's a sequence in place that gets us all the way down to 6,800. We've found this question to be a bust in cases, particularly in DX units. We've had cases where the DX units are set with a manufacturer limit of 50% turn down. So a 25,000 CFM unit wouldn't be able to turn down any further than 12,000 CFM. So we need to do this viability check. Last example is to take a look at a boiler system. Here, this is a 220,000 square foot project, so it's quite a big project. 3 boilers that are 25 million BTU each. So if we ran all 3 boilers, we'd be at 33 BTU per square foot. If we run 2 boilers, assuming this is N+1, we'd be at 22 BTU per square foot. And even if we run 1 boiler, we're at 11 BTU per square foot. Well, our heating energy target is 1 BTU per square foot, which is 9% of 1 boiler. That's our heating target at 75 degrees, which means that unless this 1 boiler is capable of doing better than a 10-to-1 turn down, then this boiler system really won't even be capable of operating at our energy target. That's problematic. Even if the system does have higher demand in it right now, we would want to make sure that we're selecting equipment that is going to be capable of getting us to these energy targets over the course of their life. So to sum up on this section, we now have published energy targets for the work in existing buildings. Doesn't necessarily mean that every project has to meet those projects, but we always need to check against them in our design and articulate where we are relative to them. So that will take us to our last section. In this section, we're going to talk about benchmarking and cooling loads and load diversities. Our design program requires that the engineer of record needs to provide load calculations, and we want those load calculations to be relatable to the historical loads. Now, if you haven't heard the phrase or the word historical load, then I want you to please become familiar with it. In fact, if you're an HVAC engineer doing work for Kaiser, I'm afraid I must insist that you start talking about historical loads and you start using the word historical loads in a sentence. We have an ASHRAE peer-reviewed transaction paper that is through peer review, actually waiting for publication in summer 2022. So we can't actually distribute that in paper form, but we did record a presentation version of it and made that public. I think we've sent that out to everyone. If anybody else needs it, then let us know. You can watch it in your office as a lunch and learn or whatever, but you need to understand the nature of the work that's going on there. Most importantly, you need to be able to ready to repeat that process. If you are working on a room that's not in this list of rooms, then we can send you historical data for 10 or 20 of those rooms and use that to determine the historical loads. So HVAC engineers have always calculated heat flows and loads based on sets of assumptions. And that's great. That's what we've always done. That's what our handbooks are written around. But once we have historical loads, we have to give those historical loads a higher weight. And I want to be very clear about this. If your design calculation based on assumptions says that your operating room load is going to be 40,000 BTU, and our historical data from all operating rooms shows that it's never going to be more than 22,000 BTU, then your calculations are wrong. Or I think the better way to say that is that the assumptions of the calculation need to be adjusted. They need to be calibrated to match the historical data. That was always the intent of the load calculations to begin with. So the first set of data that we have from this project is the room peak loads. You can see we have a list of room types and we've been able to determine the historical peak load. And we need to relate those back to our calculation. To relate them, the room peak load is the sensible load, and it's the sum of the envelope load plus the internal load. It does not include system loads or ventilation loads or anything that's outside the room. So we want to check our room peaks against those historical loads. And by the way, if you haven't checked through these numbers, the room peak loads are pretty much where we thought they were going to be. In other words, we've kind of been getting those right for the most part across the years. The big impact comes in the block peak loads. So because no two rooms actually peak at the same time, so once you get to more than 3 or 4 rooms of any type on a system, the loads diversify pretty quickly into the overall sum. And so again, we would compare these block peak loads to our load calculations. They are space loads, so they include envelope and they include internal loads, and not ventilation, not system loads. So what we've done is this little data project where we were able to cross-pollinate these loads with a list that we have from another project. Back in 2019, every time an air handling system got done in KP, we put every room into this database. And so we have a giant database of rooms. It's rooms and areas and how they fit into standard 170 and table 4A. But it's a giant database, 750,000 square foot, 24 different air handling units. So what we did was merge that data together, take the diversified block loads and merge them with this data. That gives us an idea of what these overall systems should look like in a set of KP buildings, a set of 25 air handling projects. So what's the range of diversified space load that we should expect to incur? And you can see the biggest number on that list is about 10.5 BTU per square foot. And yes, that is the system that has operating rooms. And then the lowest number on the list is 6.7 BTU per square foot. So that really suggests a rule of thumb here. About 2/3 of these systems come up with a block peak space load that's less than 8.5 BTU per square foot. And so that's the number that we're going to start to use to check systems during design. If the block peak space load is higher than 8.5 BTU per square foot, that means that we need to take a look at what the assumptions are for diversity. So let's look at an example. This is a 22,000 square foot project. The block peak space sensible load is 10.1 BTU per square foot. That's about 20% over that benchmark. So unless the system serves overall ORs, that's probably high. And when we dive in a little deeper, we can quickly see where that's at. It's internally load driven, and with just a few calculations, we can see the lighting load is high, the miscellaneous load assumption is also high, and the number of people in the system is way too high. By the way, if you don't know, Kaiser standard is 5 parking spaces per 1,000 square foot. So 200 square foot per person in a system means that the parking lot is 100% full. And if the parking lot is 80% full, that'd be more like 250 square foot per person. So a much better assumption, right? Second example, very similar story. This is a 31,000 square foot system. The block peak sensible load is 13.7 BTU per square foot, which is about 50% over the benchmark. So again, this one is high, and it's internally load driven. That's an interesting thing that I found here. When we talk to design engineers about these historical loads, the main concern is the weather. They say, what if my building is in a climate where it's 150 degrees? And yet when we look at load calculations, internal load is usually the driver. If this building was in a climate where it's 150 degrees, we can correct for that. That's pretty easy. But in this case, the internal load is what's driving it. And again, we can see the lighting assumption is too high, the miscellaneous load assumption is too high, and the number of people in this case is way too high. So what our design checking process is going to be, as a general rule here, we'll check against this number, 8.5 BTU per square foot, just as a benchmark, as a general benchmark. So here's the process. If the BOD doesn't have load calculations in it, then we're going to send it back to you right away. That should always be the case. If the BOD has load calculations in it and the block peak loads are higher than 8.5 BTU per square foot, then we want to essentially audit it. We want to have an open conversation about the room-to-room diversity in the design, look at the list of rooms, look at the diversity factors, and see what you've actually assumed there. So in closing, we are now looking at historical loads. If you're a design engineer in the Kaiser program, we want you to understand historical loads, and we're definitely fixating on the idea of historical load diversity. Please review the historical load conversation and be familiar with this as a design checking requirement. That is the end of this section, and that is the end of the show.